This video will cover Chapter 11, DC Circuit Inductance, from the AC/DC Principles and Applications, published by Advanced Technical Publications, ATP, 2nd edition. What we're going to be talking about in this chapter is inductance. Inductance is symbolized by L, and it is measured in henries. Henries is abbreviated with a capital letter H. We're going to talk about factors affecting inductance, inductive, resistive circuits, mutual inductance. This is the principle by which transformers operate. We're going to look at inductors connected in series and inductors connected in parallel. One thing that you must remember, very essential and important, is that DC circuits have 0 ohms of inductive reactance. Now they do have resistance, but they have no reactance. Also remember that reactance and resistance are both measured in ohms. So the first thing we need to understand is, what is inductance? Here's the short definition. The ability to induce voltage. That's what inductance is. A little bit longer definition. Inductance is the ability of a conductor or coil to induce voltage. The ability of one coil with an electromagnetic field around it to induce in a second coil voltage. Inductance, the unit of which is the Henry. The Henry is a unit of electrical induction, or a unit of measure, is a unit of measure of the ability of a coil to induce voltage in another conductor or in itself. The Henry uses magnetism to induce, but the Henry is not a unit of magnetism. It is a unit of inductance. So the short definition for inductance is the ability to induce voltage. Now we've already looked at how anytime there is electrical current that travels through a wire, there will be a corresponding magnetic field around that wire. We talked about that in our first lecture. I've got another slide for you here, and you can see how in this slide you've got a DC current going through this wire because it's only going in one direction, so we know that it is DC, and within that DC coil is created a magnetic field, and that magnetic field will have a polarity. We're also going to talk about how inductors in series add up. They add up just like resistance in series, or if we have inductors in parallel, the inductance adds up just like the reciprocal formula that we used for resistors in parallel. So this ability of a coil to induce voltage. Now I'm distinguishing this from the magnetic power to pick something up. That was measured in ampere turns. MMF is equal to I times N. Whereas this measurement of henries is its ability to induce voltage. So we're going to do many calculations with inductors in series and inductors in parallel. Here again you see a DC coil. See the DC current going through the coil. You see the magnetic polarity of the field inside of the coil. Now this is important, and one of the most common uses of this principle. Where do we apply this principle? The practical application of this principle would be used in a component like this. This is a solenoid valve. So in this instance the electricity is on. It pulls the plunger towards the coil. It pulls the plunger in like this. Boom. When the electricity is removed, though, this spring right here forces the plunger back down. So if our pipe was here, obviously the water could not flow through when the plunger's down. It could only flow through when the plunger's up. Our process may be something other than water. Obviously it could be anything. We'll call it our process. Our process could flow through when it was up. Spring-loaded mechanical energy makes it go back down. Now let's see one in circuit or in process. Here we see where you have a DC current, and a solenoid is only going to work with DC. Just like a relay is only going to work with DC. When this is closed in this state like it is right here, now it's open, now it's closed, with both of these contacts being connected, it sends an electrical signal through this magnetic field, and that will draw up this plunger made of metal. It's attracted to the magnetic field. This compresses the spring and it opens the valve. Once the valve is open, process can flow. When the contacts are opened up, magnetic field disappears, and the compressed spring can use mechanical energy again to close the valve. On this chart that's in your book, you see many of the factors that will affect the coil. How many windings you have around the coil, how they're spaced, the diameter of the core itself, the shape of the core, the number of layers of the core, the type of material it's made out of, and its permeability. There's a certain type of magnetic core called a toroid, and in this instance, due to the physical structure of this type of a coil, the magnetic field remains within this circle. It does not escape this circle. It remains within this circle. Whereas if you had a coil like this, then the magnetic field is going to come outside of the coil as it comes back into the south pole of the magnet. There is also color-coded inductors. The color code here is the same as the color code for resistance. Another type of inductor that is very important to understand is the shielded inductor. And this is an inductor inside of this metal case. This metal case acts like a shield, and it keeps the magnetic field of this coil, of this core, from escaping and influencing other components around this coil. Now let's look at three different types of circuits here. In the first circuit, this is the type of circuit we've been dealing with. It has resistance only, which is measured in ohms. The next one here, we see it has only coils. So in a circuit like this, with only inductors, you would have XL for inductive reactance. Now in the third one here, you have both resistance and you have reactance, and when you combine those two together, it's called impedance, symbolized by Z. And the good thing is they're all measured in ohms. All three of them are measured in ohms. They are all forms of opposition to current flow, but they do have three different names: impedance, reactance, and resistance. The formula for inductive reactance is XL is equal to 2 pi FL. Definitely need to write this down. It is not in your book. The higher the frequency, the F of the AC, the greater the L, the higher the XL, which is your inductive reactance. Remember, no XL for a steady DC current. Here they're showing us a resistive circuit, the type that we've been dealing with, which this is a good chart from your book because it shows you, in order to measure, first of all, current, here you have to be in series, you have to break into the circuit. But to measure voltage, you can just be in parallel with your resistor, for instance, and you can measure the voltage in parallel. The other thing to take note of on this chart is what they're showing you is current flow. So when you flip the light switch on, for instance, the current flow is immediately, let's say, I think it's 5 amps, and it'll stay at 5 amps until you turn the switch off, until you open the switch. When you open the switch, it immediately collapses. It immediately goes to max, immediately collapses. But when you have an inductive circuit in here, due to the fact that an inductor can hold some electrical charge, and it takes it a few minutes to turn, to ramp up, you don't have an instantaneous current. You have a collapsing current when you turn it off. It takes a little time. You have a ramping up current when you turn it on. Another important topic that we have to discuss is mutual inductance. And mutual inductance is when I have a coil here that has some inductance. What they're showing you here basically is a transformer utility coupling. This would be a permeable metal that would have a magnetic field rotating within it. I would take one wire here from my primary side. I would send a voltage through it. It has to be an AC voltage though. And on this side I would have my secondary, and this magnetic field expanding and collapsing would cause this second coil to also have a voltage induced into it. And we're going to do some math on transformers. The only thing I want you to remember right now is that mutual inductance is the principle by which transformers work. Okay, here's an example of a transformer from a circuit. You've got your primary and your secondary windings. This is the formula for finding the secondary voltage of a transformer. Vs is equal to NS over NP times VP. The voltage of the secondary is equal to the number of the windings of the secondary over the number of the windings of the primary times the voltage of the primary. You need to remember that formula. Now, a transformer can step up or step down the voltage level from the AC source using the concept of mutual inductance. So here on the primary side you have fewer windings than you have on the secondary side, so you're stepping up the voltage. In this instance though, you have more on the primary than you do on the secondary, so you're stepping down the volt. Now typically when we draw these, we're just going to draw them with the same number of windings on each side, like this circuit here. That's all you need to worry about as far as drawing a transformer circuit is concerned. So for instance here we put in 120 volts, we're stepping it up 1 to 3. So 120, 240, 360, we step it up times 3, and this we can get 360 volts across our load. Here again, putting in 120 volts, same input, but we're stepping it down 3 to 1. So here we stepped it down to 40 volts. It's just a ratio of step up or step down. From your book here, they're showing you another way to look at when you have two coils in series, and here is your formula for that as I showed you before. Here is the ones in parallel, and remember you have to use the reciprocal formula for coils in parallel. The next thing that we're going to do, if we haven't done it already in class, is we're going to do my review questions that I write from my student handout that I will provide you in class. Remember that some of the questions come from your chapter reading and some of them come from the notes that you take from my lecture, whether it be this lecture now or whether it be the in-class